Alright, so for anyone who's going to watch this later, final exam will have two parts. Part 1 will be short answer. There's no partial credit. So things like multiple choice, true false, and fill in the blank, things like that. And then the second part is free response, so you will have space to work out the problems. And the topics there will be just mainly three things: working out limits, right? Cancellation, rationalizing, things like that. All the derivative rules that we talked about, product, quotient, chain rule, and then the new stuff, right? Integration, U substitution, all those techniques. So this will be the bulk of part 2. And calculator is allowed on both halves, so there is no distinction there. You can use the TI-84 on both halves. Alright, so basically I wanted to use this time for you guys. If you flip through the final exam preparation, there's all sorts of problems, and I could point out the ones that are most difficult, that I recognize that are most difficult for students, but if you have had a chance to look at it and you know of ones that you're bothered by, I mean, we could do those. It doesn't matter to me. So this is broken up via the units, so they talk about chapter 2, which is all about limits. And then I believe the next 2 units, derivatives, and then also the graphical applications, they blend that together. That starts with number 10. And then the last unit begins with number 29. And like I told you guys for the video, I'm going to stay between these two vertical lines so that way we can film. So ready, set, go. What questions do you guys have, or would you rather I pick them? I don't really got it.
Any questions concerning U substitution?
Okay, so, and this is the other thing, is you can pick whatever you want. We don't have to go chronological. All right.
I'm sorry, I haven't looked over it, so I can't do this.
That is, I will pick one. Okay, so the question here was to pick anything with U substitution, so that's the new stuff in Unit 5. So I'm going to talk about 29. That's kind of late. 29E. All right. Just make sure. Okay. All right. So I am in a room full of calculus students, right? So, and many of you probably just took the test on this content. So this is a basic indefinite integral, go backwards and find the antiderivative. So there is an optimal choice here for you, and I want to ask you guys if you know what it is. I can pick it, but you guys have to think about it, right? What do you pick here? Arctan is definitely the choice. And Sarah, right? What's the reason for that? Why is that a good choice?
It's in parentheses?
Yeah, it's in parentheses, but there's another, that's one thing, but there's something else that would suggest it's going to work well.
Isn't,
You don't have to raise your hand.
okay. Isn't the derivative of it going to end up being 1?
It's right there in the problem, right? So the derivative of arctan is hiding in the problem. So if you look carefully, you can always put a 1 here, right? So this is the derivative of arctan. So this is going to go from a complicated looking problem to something that's pretty simple. So let's do du dx here. Okay, so this is the derivative of the arctan function, and then you can swing the dx over to the right. Okay, so when I normally teach this in class, I put these things in boxes here, where this is the original choice that we made in the problem, and this is the other thing here, right, the derivative. So both of these pieces are relevant in going into this problem, and you can turn this into a pretty straightforward problem. Okay, so I'm going to rewrite this here for you guys. So arctan is u, so this will be u to the 3rd power. Right, that 3 is the only part that we didn't touch in the problem. And then this 1 over 1 plus x squared dx is replaceable by du. Right? So that's the huge step. That's the toughest part of the problem. Once you've turned this into this, the problem with u is very straightforward. just a basic power rule. Okay, so surprisingly here, the easiest part of this problem is the integration, right? It's the part where you actually use the power rule. So your answer is here, and you put arctangent of x back in for u.
Where did the du go?
All right, well the du is something that works in a dynamical way with this, right? So this is the part that you're actually integrating. So it's a power function, so you just increase the power by 1.
Yeah, so
Yeah, du's gone.
so du on its own can like function as like whatever it's like with, you
Yeah.
integrate it.
There's a deeper meaning later on in Calc 2. For now, we could say this is something that just indicates the variable of integration. So we're integrating with respect to u, so our answer comes out with respect to u. So I'm going to put this back in here, and then give you guys the answer. Okay, that's it. And that one's done. Good, bad? All right. You still look like you're...
I just I'm trying to figure out how.
Is it
Okay,
the
so
DU
like-
part, or?
I was kind of having that same issue, like understanding like, okay, so if this like thing that we just solved for turns into du, where does du go?
Right.
Yeah,
when you
Okay,
integrate?
I
I
gotcha.
don't
So
see
you
that.
guys are asking a good question because it's a very, it's kind of a deep theoretical thing that
Mhm.
you, if you see an application, you can see how these two actually work together. But if you look at the theorems that we've talked about, remember in some of the notes we talked about little f and capital F? So this is saying integrate a function, right, and you get the antiderivative. And the meaning behind this is that when you differentiate this one, you get that one back. So the whole thing about talking about this, you could discuss a relationship between these two functions. And notice in the whole time that you talk about that, you don't really talk about this, right? So that's not something that we're really talking about in terms of switching, right? Function and antiderivative. So really this is the function that you're looking at, and you seek the antiderivative, and in this case, this one here, and the way you can check that is differentiate this, and this is going to come back, right, as your answer.
Can we go over like something with the implicit differentiation
Sure, those
and
are hard.
related rates?
Yep. So you want me to identify, or can you identify? I can pick them out for you, but it's good when...
Yeah, there was like the one on, I forget if it was exam 2 or exam 3 with like the, I think it was like a sliding ladder
Yep.
or something.
Okay. Okay, so implicit, I'll do one from number 10 first, and then we'll do that. So definitely feel free at any point to ask questions. You know, this is, I don't want to lecture you, you know, just ask whatever you like. So number 10, implicit, let's see. I see a couple of them. I'm going to do letter I. So can anyone explain a number 10, letter I? I'll write this one down for you. So this involves implicit differentiation, a different technique. And what's the reason for that? So why does this one not fit the mold of different problems? Yeah, it's the two variables. This here is not written in the explicit form where you have y as a function of x, so you can identify y in a couple of different locations. And if it's difficult to isolate the y, then you would leave this the way it is and just differentiate both sides. So I'm going to do that here. So differentiate the left and also the right. And then you're going to have a bunch of y primes or dy dx's floating around in the problem, and then you end up solving for that. All right. So what's the rule that you need for the first one?
X or
Well, I'm pointing to this whole thing.
X turn 1, e to the y would stay e to the y.
That's close, but
Oh.
you need a specific rule here.
Chain rule.
Chain rule, you need one more. Ready?
Isn't that, is x going to be a constant?
Product rule.
Oh.
Okay, this dot.
Oh, yeah.
So this is x times e to the y, so you need the product rule in there, and then also the chain rule. So to get this first one, the first function and differentiate the second. Okay, so x is your first and e to the y is your second. So you write down your first and you differentiate your second. You have to differentiate the exponent, so y gives you y prime, and then you add the opposite, the second function, and differentiate the first. So write down e to the y, the derivative of x is 1, and so that part's done. And then 1 will differentiate to nothing. Just go right through the equal sign, and then you have xy. Okay, and you have the product rule again here on the right-hand side. So even if you don't see the multiplication, you can make it explicit with the dot. So as a calc teacher, I can tell you that 99.9% of all mistakes occur right here. So if you can get to this point, most people can finish it, right? Because you have to isolate y prime and solve for it. So
I'm confused about that first part of the product rule. Why did that turn x e to the y prime?
okay, so there are two parts. There's this part and this one,
Yeah.
right? So it is the first one right there, okay? And then you differentiate the second. But y is a function of x, so e to the y comes back, and then you have to differentiate the exponent. So the derivative of y is dy dx or y prime. Okay, this is because this goes back to the stuff that was discussed many weeks ago. The derivative is with respect to x. Anything else on that? Okay, so to finish it, you would look at the places you have a y prime here and there. So the goal is just collect them on one side together and then solve, and you're finished. So I'm going to move this to the left and simultaneously move this to the right. Just going to move some terms. Okay. So you're going to have a couple of negatives show up, right? So xy prime is negative on the left, and then e to the y is negative on the right. And this problem's almost done. You can factor out y prime. That. This is just going to be brought down, and then your answer is pretty much there, right? So the derivative is going to equal y minus e to the y on the right, and then you're going to divide by this. I'll put that here. Okay. And like is mentioned early on in the notes, often your answer has x's and y's in it together, and you can see that right there. So the other ones, if you guys want to try them, can I find them here? F.
I'm so
F is another one that has implicit differentiation. And I think that's it. C. So F, C, and I are all similar, right? You'd use the same kind of technique to solve those. Is this still humming along?
It looks like it, yeah.
Because it's been known to shut off after like 25 minutes. It's like, okay, I'm done. And then I just have to turn it back on.
14 so far, so we'll see.
Awesome. Okay. Now you want also related rate. Okay, I on 15. Okay. So number 15, we're going to drop a pebble into a pond, and you're going to see those concentric circles, right? The circles grow out. So this is the imagery here. Who hasn't done this as a kid, right? You watch it happen. Okay, so this problem is about how the radius is changing, right, as that outer circle is growing. And so they give you some data in this problem, and then they ask you a specific question. All right, so let's read this here. So it says the radius of the outer ripple is increasing at a constant rate of 1/2 foot per second. So I'm going to write this down. This is dr dt. So this is the rate, right, at which the radius is changing with respect to time. So dr dt, and so this is 1/2 foot per second. That's given in the problem. And so then the question says when the radius is 4 feet. So I'm going to write that down verbatim. So at the moment when r is 4 feet, it says at what rate is the total area of the disturbed water changing? So they're asking you for dA dt. So I gotta tell you, this problem for related rates is very cookbook. It's very kind of standard where you have a pretty simple model. They give you a couple of pieces of information and then they ask you for another thing. So who remembers how to get this rolling? There's an equation, right?
Yeah, and it's,
Okay, so what do you need?
well, do you need the velocity at 0, or the starting velocity?
Well,
It's the area of the circle.
It's the area of the circle, right?
Just
This
kidding,
problem,
I'm sorry.
okay, it's all about the total area. So you need one thing here, just the area is pi r squared, right? And the moment you write that down, you could tell A and R, right? All those things are kind of relevant in this problem, okay? So the place where these are different is we differentiate with respect to time. So time is your independent variable. So all of your derivatives look like this, right? d by dt, because your independent variable is time. So we're going to differentiate the left and then also the right with respect to t. So I am going through these kind of quickly because you should be familiar with these things, but if something catches you, you can just ask about it, right? So this would be dA dt, okay? And pi is constant, right? But r squared becomes 2r to the first power, right? But then r is something that depends on time. So as time goes by, your radius changes. So this is the chain rule. I know you see my all caps, all bold font, right, in an online course. The chain rule is the most important rule in the class, right, for derivatives. So you need it for related rates. So this is what you get out of this, and then the question is all about this, right? How is the area of the disturbed water changing? So it's really a matter of just inserting the correct info where it belongs, and then solving. So this is 2 pi r dr dt. And so notice dr dt is given in the problem, right? 1/2 foot per second. So it's simple once we have all of that info. The radius is 4. Dr dt is 1/2 foot per second. Okay. So this looks like it's going to be 4 pi, right? So that's around 12, right? The interpretation there. And what are the units on that? Oh wait, is that right? At what rate? Oh yeah, the rate should be feet squared per second. So it's actually none of those. right? But I guess you get the idea. Okay, so the rate should be in square feet per second because we're talking about area. So for that one, we would pick C. But this is a good one to understand. It is kind of a simple one, but once you understand the process of related rates, they're all sort of similar problems. You have a question? You want to ask one? Should bounce around. You've gotten your fill, right? A couple of good ones. We can come back. Yep.
Can you, okay, so limits, derivatives, integrals.
In integrals. So
Can you give like a description, a word description on like what's like the main object? Like a general overview.
well, I can tell you the exact problem number that relates to those sections.
No, like how like a derivative, the main point of a derivative is to find like the tangent.
Oh, you mean like the meaning behind it?
Yeah,
Oh.
exactly.
Okay,
You
that's
just
an
say,
interesting
like-
question.
I know.
That's good. No, that's good. Well, the way this course is designed, I mean, do you want me to write it down or just talk about it?
You
Okay,
can
the way the
just-
course is designed is that they talk about limits first because it's used to define the derivative and also the integral. Because the limit is used as h goes to 0 to define the slope of the tangent line. So the derivative geometrically is the slope of the tangent line or the velocity of a particle if the actual function means position. So it depends on the context of the function. So if it's just a mathematical function, then the derivative is the steepness of the line that just touches the curve at one particular point. Or it could mean how fast something is moving. For the integral, the basic interpretation would be the area underneath the curve. So when you integrate from a lower point A to an upper point B, and you go backwards, the antiderivative is the area between A and B underneath that function.
It's so weird how.
It's very weird. It's because they don't
Yeah.
seem to be opposites, but
Yeah.
if you read kind of the history behind them, the slope is like a division problem, change in y over change in x. So you
Okay,
think
yeah.
about division, and if you think about area using rectangles, it's actually a multiplication problem, length times width. When you multiply two things, it's inversely related to division. So there are actually connections there. That's for another day. That's for a YouTube video. Yep.
Going over that, not really actually, but on a past exam, I think it was not this one, but exam 3, there was a problem, like, look at this graph, sketch what you think would be the...
Do you want to do one of those?
Yeah, because I had no idea
Okay.
how to just like hide that.
Here we can make one up.
Yeah.
And someone else can be in the video because you can go. No. Okay, so I'll make one up.
I might be able to pull out that one, actually.
Right, that's fine. I'll tell you what, I won't make it crazy, too difficult for me or you. But yeah, this is really a conceptual type of question, kind of like what you were asking. So if this graph is the graph of f, right, some function, the tricky thing about this is you don't have the formula for f. All you have is the shape, right? And then you could be asked to sketch roughly, right, f prime. So there's no human being that I know that could actually just do this. You have to do it piecemeal, right? So you really have to think about the function, think about what it's doing, right? And you can think of those things that we talked about. It's rising, it's falling, it's rising, right? And things like mins and maxes. And all of those things give you information or are connected to f prime. So who can give one little piece here? Because it really is a piecemeal deal. You have to bring all the pieces together.
Where it like intercepts the x-axis, you know that the derivative is gonna intercept at the same point, such as 0 and those other two ones.
Okay, so we talking about these here?
Yes.
Right. Say that one more time.
where the function
Mhm.
crosses the x-axis,
Right.
we know that the derivative is gonna like go through the same point, like touch the same point.
I don't know for sure that we can say that.
Really?
I think you're trying to say something that,
Or go through the origin at least. Like touch the 0? No?
okay, let's do this, ready? I'll challenge that thought.
Okay.
So put a tangent line in here, right? Because this is what the derivative is, it's the slope.
Mhm.
What would you estimate is the slope of that line? Just, I mean, you don't have to be close, but it's positive, right?
Yeah.
So the slope might be something like 2. So what this means is if you're sketching this, the output of the derivative would be 2. So right at this point, your function would be up there. That's where f prime would be, so it wouldn't be passing through necessarily at that point.
Okay. But
Now-
it has to like touch the same point, like be. Because when I was studying for. Okay,
Yeah,
maybe.
but the thing is, I can feel the fire because what you're trying to say is something that is very important because.
Okay.
Sure.
Can I just make a wild guess?
I guess so. I can't stop you.
Can the points of inflection help you at all?
They can, but that's for inflection points
I
are
guess
about
that-
f
yeah,
double
that's-
prime.
yeah.
So that's like your brain.
I'm
like,
just looking off this one.
Okay, right.
It's pretty much all about like the slopes increasing and
Yes,
decreasing.
right. So basically, you're talking a lot about the x-axis.
Yeah.
So the question I'll go off of that is where would the derivative pass through the x-axis? Because that's a very good question to ask yourself. Because if the derivative passes through the x-axis, then that means the slope is what number?
0.
0. So you're asking yourself,
Oh, yeah.
where is the slope 0? Where does that happen?
That would be like at the relative maximum.
You
and
got
minimum,
it,
right?
right here. So if you look at the hill of the function, right here, okay, anytime a function hits the max or the min, that corresponds to a critical number. So at this point, you could say the derivative is definitely going to go through the x-axis there, right? And that's what you're trying to say, I think,
Yeah,
right? So
yes.
that's why you were thinking along the right path. Now down here, the minimum, this is also a critical number because f prime is 0. So these 2 green dots on the x-axis are definitely going to be points that are directly on f prime.
It's kind of what I meant. I used
Oh,
the wrong term.
okay,
'Cause it
inflection points are different.
Yeah, it
Right.
is. I used the wrong term. in this one.
Okay. Okay. And so what we're doing is we're just kind of building together f prime, what it looks like. So I'm going to put some dotted lines here to break this into regions. Okay. So the slope right to the left of the first green dot is always positive, right? So you could tell that your derivative graph has to be above the x-axis. So we're positive on this side, okay? How can you describe in one word the slope between the 2 green dots? That's 0. It's negative. And so if you put a slope tangent line here, anywhere between the 2 green dots, the commonality is they're all falling from left to right. Right? So the slope is negative. Put a negative here, and then it switches on the other side. Okay. So the slope is positive, negative, and then positive. So I'm going to use that red dot that we had there, and so the graph, it doesn't have to be perfect, but it's going to look something like this. Okay, you see that the outputs are positive, negative underneath the x-axis, and then positive again. And so that's a rough sketch of f prime. Okay, you would not be wrong. I would give you full credit if you sketch something like this, because it has the same attributes, right? Something you can't tell is the exact slope, but if you have the rough shape of it, then that means you have the idea down. Okay, and what should make sense here is that the black curve almost looks like a cubic function. When you differentiate a cubic function, what kind of function do you get?
The square.
Quadratic, right? So you get a parabola. So you can see it in the shape, right? The way that the graphs look.
That's a good way to think about it.
Very
Way
good.
more helpful.
Yeah. There's always 6 different ways in math to do the same thing, but this is a good problem.